Hi, this video is an overview of the binary trees and how they're used in our class, and touching a little bit on the project that we're going to be doing on binary trees, although there's a separate code walkthrough video coming for that, so you will also want to view that. In this video, I'm going to talk about how trees fit into the larger scheme of things. And so let me get started with that presentation, and we'll go from there. I'm going to share my screen. And start the presentation. Okay, this is an overview of binary trees. Those are the first structure we've talked about that makes extensive use of links rather than direct address calculation. So I want to explain to you where trees fit in this typology of data structures that we're learning in class, because there are a lot of possible data structures, and just trying to memorize a list of all the possible data structures that you could use and which ones are built into Python and which ones aren't is not particularly useful to you as an application developer. In fact, what's a lot more useful is to have a conceptual framework for thinking about data structures, so you can think about what data structure, which data structure, would be the most appropriate for the problem I'm trying to solve. That's why this is, of course, in applied data structures. In order to learn about those data structures, though, of course, we have to look somewhat into the theory. And that comes from the Zybook, and that comes from the practice projects that we're doing like right now. When we talked about arrays, the first fundamental data structure we talked about a structure where you can find an element directly from an integer index. And that uses address calculation. The code figures out where the start of the array is, multiplies by the size of the elements, and goes directly to that element. If that's unclear, you can review that video. Hashing is also an indirect form of address calculation. A hash table really is an array, just as a list is an array. And the buckets in an array are elements, like the elements in an array. The difference is, one of the major differences, is that the hashing allows non-integer value keys, and the compression of the key space that's required in order to support that brings up lots of other problems like collision resolution that you have to deal with, which you don't have to deal with if you're just dealing with an array or a list. So it's really two families of data structures that we're talking about so far. Trees are the first linked structure that we examined. So instead of calculating where an element is directly, which is order 1, trees figure out where the desired element is or is to be inserted by following references from a root down to towards the leaves of the tree to find out where to insert or return an element. So you're following links, and see, these would be pointers. You're following links to get what you want rather than going directly to it. That means trade-off. So when trees are balanced, we'll talk more in a minute about what that means. Binary trees offer order log 2 in performance. In other words, they're not as good as order 1, of course, but the log 2 of the number of items is growing very slowly. Essentially, as you double the number of items in a binary tree, you're only increasing n by 1. So it is a less efficient scheme for searching than going directly in an array or even using a hash table, but it is still a efficient search structure and is commonly used that way. It's much better than the order n you would get if you tried to simply search through an array to find a matching element. There's a link in here from Stack Overflow, which gives a really good description of why they figured out and how you can understand that trees offer order log n2 performance. Here's a picture, a diagram, of an idealized binary tree. These are the kind you see in texts and introductory web presentations. The gray squares are the nodes. Obviously, that's where the values that are being kept in the tree reside, along with pointers to the references, so we'll say pointers, to the left and right, which are links that take you to the next element in the tree. This tree is perfectly balanced. It's symmetrical all the way down. On each side of the head or root, there are an equal number of nodes, and coming down one level to the middle level, those also have an equal number of child nodes. So those nodes at the bottom are called leaves, following the tree analogy, right? So the tree's actually upside down, if you haven't figured it out yet, with the trunk or the head of the tree up in the air and the leaves on the ground. It's sort of like what happens to trees after a hurricane, but it's a lot easier to draw and understand somehow hierarchically if you put the root at the top. So that's the idealized picture. Here's a slightly less idealized picture of a more realistic schematic tree. It's still got the same elements. It's got a root or head pointer. It's got the nodes, which are the gray boxes. It's got left and right links, but you can see it's asymmetrical. It's not balanced anymore. There are a lot more nodes on the left link than on the right, and there are some nodes where there aren't any, like on the second row, there is no right link. There's no element there, and there's only one leaf on the bottom. So searching this tree, it won't be order log 2 in. It's not good. This unbalancing makes the search somewhat less efficient, but it'll still be a lot more efficient than searching through those nodes sequentially. This shows you a much more realistic sort of tree. This is a diagram. It's actually drawn from the code that you'll be working with for this project, and I found on the internet a cool little routine that will actually go through your tree after you build it with your code and draw this diagram showing you the basic structure of the tree. Now, in this diagram, instead of the tree being upside down, it's turned to the left, so it's fallen over. And the root is actually the star Sol up in the upper left-hand corner. You may or may not remember, if you're taking an astronomy class, that's the official name for our sun. And coming off of that, you can see all of these links following left and right, and all of the subtrees that are connected together. The names of the nodes here are the names of stars, and we'll talk a little bit about that in the future, but that's not critical to understanding what's going on. Any data would do. It's just interesting data. So now that's one tree that's possible from this data set. But it turns out that in an unbalanced tree, the order in which you add elements to the tree, nodes to the tree, makes a difference in the shape of the tree. This one started out, kind of an unfortunate case, with Sol, which is the greatest, they're in alphabetical order. So this is the last one in alphabetical order. That turned out to be the root. So of course, everything hangs off the left side of Sol because there's no names in this short star database whose ASCII value is greater than SOL. If you scramble the data first into a different order, and then you draw the tree, you're going to get something that looks a little bit different. This one has a different root, and I lost the sun somewhere. That may be a bad thing for Earth, I don't know. But you can see the structure here. The root is now at the very bottom left-hand corner. That's 61 Cygni. And everything, since that's a very low, it's very early in the alphabetic sequence, everything to the right of that everything is on the right-hand link. And then there are all these subtrees off of that. So basically, the time required to search an unbalanced tree is partially dependent on how balanced it ended up being just at random. And what balancing algorithms do, something we'll look at in a different project, is they rearrange the tree so it's much more equal in terms of left and right pointers, which helps it approach the order in log 2 performance a lot better. Still, even though this isn't gonna search with log 2 in performance, it will, in fact, you can see it's still pretty efficient because every time you make a comparison, you're cutting out roughly half of the alternatives. So you can get to the thing you want. Say you want this leaf called GL447. That's almost in the middle of the screen. You start out with the root, and you have to make 1, 2, 3, 4, 5 comparisons to get there, I think. It might be off by 1. That's still a lot quicker. There are 35 names in this tree. So that's going to be a lot more efficient than just searching it in a linear array or list. So you'll see more of these diagrams when you run the program and get to see the output of the tree that you create. Let's talk about how nodes get into the tree in the first place, the insertion algorithm. This is all discussed in the Zybook. And in fact, in the project starter code, you'll see I've put in references to the Zybook and even pasted in some of their pseudocode here and there to help you out. Well, you always start at the root, the head. That's for any insertions or searches. If the root is none, or it's null, depending on what language you characterize this in, then you're done. This node, the root, the tree's empty, and you can take the node you want to add, make it the root, and you're done. That's a special case of kind of starting up. That's what's going to happen with the very first node. If the very first node is Signy 61 or whatever, then that'll be the root. If the very first node is Sol, that'll be the root. Okay, otherwise, if the root's not empty, so there's something there, then look at the root node and compare its key against the new node we're inserting. So say you want to insert another star name. If it's less than the root's key, then try to follow the left link. If it's greater than the root's key, and this is what happened, the less than is what happened every time in this code, right? Every star name that came after that was less than Sol, so we went down the left side. In the second diagram, we started with a star that was very early in the alphabetic sequence, so everything went down the right-hand link. If we're going down the link and you below the root and you come to a null or a pointer or a link that's none, then that's the place where you insert the new node and you're done. So you're going down the tree, alternating left and right according to the values that you compare between the node in the tree and the node you want to insert. And when you finally find, you run out of nodes essentially to compare it to by hitting a node whose left or right pointer is none, then you can add it right there. That's how the tree is built. The big idea is that what happens with the trees, we're optimizing the way we build the data structure so that it will be more efficient when we search it later. We're doing more work on the insert by traversing the tree in the way we are to save time for searches. And searching is one of the main applications of binary trees. The algorithm to do this, it sounds kind of complicated step by step, is actually very straightforward, and there's a recursive implementation, which I will tell you is not necessarily easy to understand, but is extremely short. It's elegant in the computer science sense of elegant, although it may have you banging your head against the desk. The idea is that adding a node to anywhere in the tree is essentially the same operation. So a tree is a tree of subtrees of subtrees of subtrees. So that yields this recursive implementation that is very efficient and very short. That code is probably only a few lines long, and you can see how that's done in the Zybook. So you don't have to use a recursive insertion algorithm. You can do it with whiles, but it's pretty straightforward to do it recursively once you get the hang of how recursion really works. And that takes a while to get your mind around intuitively, I think. The search algorithm is pretty much like the insertion algorithm. It's got the following similarities. You start at the root. You always start at the root. You use the same sort of go left for less, go right for greater, except we add a third branch that says, hey, if the key in this node we're on in the tree matches the key we're looking for, we're done, and we can return that reference to that node because we found what we wanted. If we come to you remember in the insertion, if we came to a link that was none, that's where we were ready to insert the new node. When you're searching, as soon as you found the link that's none, you can return not found. That means the key you're searching for is not in the tree. You ran through the tree following all the left and right pointers and eventually came to a node where there were no left or right pointers left to compare. So that algorithm is almost exactly like the insertion algorithm. It too has a short recursive implementation if you so choose. Let's look at some generalizations, because when you look at the diagrams, my earlier diagrams or diagrams in books like the Zybook, they often use a single numerical value for the key. So if you look at those boxes that represent nodes in a diagram, all you see is like a number. That makes it easy maybe to explain, because everybody knows that 3 is less than 5 and 7 is greater than 5. But it also is not very realistic. What we're doing in our program is much more realistic. We're going to store an object at each node. So there's a key, and that'll be the name of the star. But in addition to that, because we're storing an object inside the node, we can keep all this other information about the star. Its magnitude, its distance, its stellar class, its other astronomical stellar characteristics that are available from this database. So we're actually storing a collection of data in the form of an object at each node. That's a much more realistic example than storing a single value. We've also been discussing, and we will continue to discuss and work on for now, binary trees. Now, that's trees with two, just a left and a right pointer, a node and 2 links. However, it's very possible and very useful to create tree-like structures that have multiple keys and multiple values per node. Some of these are called B trees, confusingly enough. A B tree is not a binary tree. And that actually is extremely useful, specifically in databases. It makes a very convenient way to represent the data in rows and columns, and we will come to that in a subsequent module. In the meantime, the next thing up after this project is to look at how to balance binary trees, how to rearrange the tree, those scrambled trees that you saw in my diagrams, in such a way that they approximate a symmetrical structure, which in turn helps the search algorithm out and the insertion algorithm out significantly. So we'll cover that in subsequent modules. That's about it. Hopefully what you've taken away from this video is that you can begin to see how trees, binary trees, fall into the linked family of structures. So they're not based on address calculation. The nodes need not be stored contiguously. They're connected by links or references from one node to another. Unlike arrays and hashes, which assumed a contiguous storage, they're adjacent to one another in memory directly, and that allowed really efficient access. Trees have less efficient access, but it's still pretty good. We've glimpsed what some realistic unbalanced trees look like. These are the trees you'll get out of your program, since right now we don't make any attempt to balance a tree. And hopefully you've begun to see how the abstract performance, that's order in stuff, of a binary search tree, how that's dependent on the structure of the tree and the subtrees. So if you get some really degenerate cases, and I provide one data file where you will find a really degenerate case, when you run that data file through your working program and have it to draw the resulting tree, you'll see it does not look very good. And I'll leave it at that. Okay, balancing helps avoid that sort of problem. Talked a little bit about algorithms for creating and searching trees, and those are covered extensively in the Zybook. And that's going to help you a lot on the project, where you're going to be asked to create an insert method, a search method, and a print method, and insert them into an existing skeletal Python program. This could be done in C, but it would be very, very tedious. And I think maybe you'd have to do that at UCF, but you won't have to do that here. And in the next video, we'll walk you through the code. I'll walk you through the code that we're using in this project and try to explain how the various classes work and how the code works to help you complete the functions or methods that you need to complete the project. Thanks a lot. I'm going to stop sharing, and I'll see you in the next